Good afternoon, everyone. So we're glad to have Dr. Ma here giving a talk. And Dr. Ma is currently a research fellow in the Department of Computer Science from University of Sheffield. He's been working on computational hearing speech, including robust speech recognition, speech processing for hearing devices, and sound localization over 10 years. So today he's going to talk about his recent work on sound localization using deep learning. So I hand over to you.
Well, thank you very much. Thank you for having me today. And it's a great pleasure to come to Manchester in this rainy day, cold. So I'm from Computer Science Department at Sheffield. So this work it was done fairly recently. We just submitted a couple of papers about this work to ACAS conference. So I should mention that Paolo Vicente is a visiting PhD student of mine who did a lot of the work, and also Professor Guy Brown is also a collaborator on this project. So today's talk is really about sound localization directly from waveforms. Can I just quickly ask how many of you know, or how much you know about sound localization? So just a little bit. Yeah, that's great. So really, so just a little bit background. That's why I'm interested in sound localization. So I'm quite interested in sort of understanding how human perceive sound in general, and human listeners, we have a remarkable ability to localize sound in a multi-source environment and in a reverberant room like this as well. So that's this is a really great book about how humans can perceive sound in this complex environment. So what I'm really interested in is borrow some ideas, inspiration from human sound localization, human speech perception, and look for some idea that we can apply to a machine so that it can understand sound. So this is a project I did a couple of years ago, where we took a camera head and put a motorized collar between the head and the shoulder, so the head of the camera, the mannequin, can rotate. So really, we are looking at how we can apply some of the human sound localization technique in the camera head by exploiting the head movement, so you can sort of perceive sound around the robot. As you see, we combine the sound with stereo vision, so the two cameras as well. So really, there's a lot of application of machine sound localization. So robotics, for example, so this is a Pepper robotic, kind of popular, quite popular right now. So to be able to interact with the environment, with other humans, you really need to be able to localize sound. And hearing aids is another great area that sound localization can be useful. So these days, hearing aids tend to have multiple microphones, which allows to, if you can localize the sound, then you can beamform the particular direction, so you become more directional microphone. Smart home, so I have a Amazon Echo at home, so every time I speak to the Echo from a distance, it can localize me, and therefore have a better understanding of my voice. Other things like self-driving cars, a lot of machine-human interactions. So really, so how we localized sound, now we have 2 years, binaural years. So, so the sound, take time for the sound to travel. So the sound will arrive to the left ear first, if the source is localized at my left-hand side. Then it will arrive at the right ear later. So the time difference between the blue and the red lines gave me some cues. The sound could be on my left-hand side. So really, that's the interaural time difference cue that humans is able to use to localize sound. Apart from time difference, there's also a level difference between the 2 ears. So because the head and the shoulder would create some so-called head shadowing effect, which means the sound arriving at my right ear will be slightly quieter than the sound perceived by my left ear, assuming the source is on the left-hand side. So apart from these interaural time different cue and interaural level different cues, there's also another very important cues is spectral cues. So this is really a monaural cue because it's created by the shape of the pinna, the shape of the head, the shoulder, so it's head-related transfer function would create a cue so that different source positions will give me a subtle spectral change. So this is like a filter which human ears auditory system is able to exploit in order to localize the source. And this is particularly important for sound localization in the elevation, so vertical sound localization. So let's just take a closer look of these cues. So firstly, the IPD, the interaural time difference. So assuming I have where's my mouse? Anyway, assuming I define the azimuth angle. So I'm talking here is the azimuth, the horizontal plane in this case. So the source in front of me is 0 degrees. So then we'll define 360 around my head. So we have the front and the rear hemisphere. The IPD really, if the source is directly in front of me, so there's no time difference. So which means the source with the sound would arrive at my left and right ear at the same time. So as the source moves to the side, so the IPD would increase in one direction. At 90 degrees, so that's where the time difference will reach the maximum. Then it will then gradually move back. So when the source is directly behind me, so at 180 degrees, the IPD becomes 0 again. Then as it moves then around my head back to the 0 degree, then it's create a curve like that. You can see the IPDs roughly moved around between the minus 0.8 milliseconds to plus 0.8 milliseconds. So that's really decided by the distance between my ears, so the size of the head. So some people may have a smaller head or a bigger head, so that will create a different sort of IPD range. ILD, on the other hand, is slightly complex. So so I'm plotting the ILD computed for different frequency sounds. Okay, so let's look at the blue line first. The blue line is a low frequency sound. You can see, again, it has this sort of curve around as the sound travels around my head, but the difference is fairly small. That's because at a low frequency, this reflection of the sound, so the ILD tend to be less robust or less reliable, less useful. But as we move to high frequency sounds, that's where the level difference become a lot bigger as a result of the head shadowing effect. So as you can see, the 1,500 Hertz, the green line, and the ILD movement is a lot bigger, and the 5,005 kilohertz one is even bigger. So this really tells us the ILD is more useful or provide more useful cues to the sound localization at the higher frequencies. So indeed, if we plot the IPD, so minus 90 is the left-hand side, 90 is right-hand side. If we plot a 3D plot of the IPD across different source atomos locations and across different frequencies, you can see for the IPDs, the movement is bigger at the low frequencies, and at the high frequencies, IPDs is fairly the movement is fairly small, and on the other hand, ILD become more useful in high frequencies. Normally, the cutoff frequencies for IPD ILDs is around 2 kilohertz. So normally we say below 2 kilohertz, IPD is more useful or provide more cues to sound localization. So we just talked about sound localization in the horizontal plane. Now we can also localize sounds in the vertical plane. So there's elevation localization. So in that case, if the sound is located on the sides, that still has different elevation would still create different IPD cues and ILD cues, right? That makes sense. But on the other hand, let's say if the sound directly located directly in front of me, so different elevations, the sound would arrive as both my ears at the same time. So there's no IPD cues and no ILD cues. Really, in this case, the IPD ILDs is become less useful. What is useful really is the monaural spectral cues. So different elevations, because the shape of the peanut is designed to create some sort of filters. So this filter shape will be different for different elevation conditions. So that sort of cues is quite subtle, but that provides enough cues for humans to localize the source in the elevation. If the source is located on the sides, different elevation would also create IPD ILDs. And this cue really is integrated together by the human auditory system to be able to localize the source. Right, so this is really a plot that shows these spectral cues. So what I'm showing you here is at different elevations. So 0 atomos, which means the source is located directly in front of me, but then at different elevations, so 0 degree, 10, 20, 30 degree. So this is the frequency response of the source. At different elevation, you can see the spectral shape are different. So that sort of cues are used by the auditory brain to make sense of the location in elevation. Right, so how do we build a machine to do the same? So we know roughly how humans localize the sound. Well, the first idea would be to directly map a IPD ILD. So if we know certain IPD ILD would correspond to certain atomos angles, then we can do a direct mapping. So that's that would be the first thing you would try. But the problem is, we talk about, the different size, people have a different sound height. So for the machine you want to build a robust machine to be able to localize sound sources. Direct mapping is not very reliable. So depending on the environment, so in anechoic conditions, for example, you may have a perfect mapping relations, but once you move to a reverberant environment like this lecture room, this reflection of the sound would really corrupt this mapping. So this is not really reliable. So I just show you an example. So this is a picture I took at DTU, so Technology University in Denmark, where they have this huge anechoic room with a 3D microphone array, speaker array. So the array around you and the array on. So that way you can just measure you can do a listening test, or you can also measure the input responses of the microphones. The good thing, this is anechoic, so you have these foams, these sort of shapes that really absorb the reflection. So if you record sound in this room, it's very dry, there's no echoes. So if we measure the IPD and ILDs in this room, so what I'm plotting here is a 2D domain. So IPD in the x-axis, ILD is along the y-axis. Then I'm plotting the frequency response of the source for different frequencies. Okay, so you can see this is the source is located directly in front of me at 0 degree azimuth. You can see it has very sort of perfect dot at 0 IPD and 0 ILD for all the frequencies. However, if we move to a reverberant room like this lecture room, you measure different sources. You compute IPD, ILD for different sources, you will find you don't get a perfect dot anymore. So depending on the sound, the level of the sound, and the type of the sound, really what you get is quite messy. You get distribution for all the data samples. Then as you move to higher frequencies, you can see this sort of ripples. So this ripples occurs for the IPDs. That's because to compute IPDs, you tend to compute the cross correlations of these two channels between left and right ears. And the cross correlation depend on the center frequencies of this filter. It has this periodic side peaks. So it's very likely you just pick the wrong peak. You pick the one that's there's the side peak rather than the actual peak that corresponds to the true IPDs. And indeed, if we just look at the so the plot I showed you in the previous slides is for 0 degree azimuth. If I plot for minus 50 degrees and plus 50 degrees, it's even messier. Even in the anechoic condition, you don't get a perfect dot. You get some sort of distribution. You get some sort of distribution for the 50 degree as well, and this is even messier for the reverberant condition. Okay, so think about you want to do a direct mapping. It's just very difficult. It doesn't work. It doesn't work reliably, at least. So what we do? Okay, so let's say we want to build a machine. We can apply some machine learning technique to learn from the data, to learn the mapping between some sort of IPD, ILD distribution to some sound azimuth. So for machine learning, you could have genetic models where you just model the distribution. So in this case, the blue circle represents using a Gaussian mixture model, for example. So this is a Gaussian distribution, a 2D Gaussian distribution. So I'm model that's one distribution. For minus 50 degree, I have a different distribution. So once I have these two distributions, then for a new data sample with a new pair of ITD, ILD, I can say which distribution gives me the highest probabilities. So that's one way to build a machine to localize sound sources by learning the mapping from the data, which tends to be more reliable than direct mapping. Another way is discriminative model. So where really we're trying to learn the boundary between these two data distribution. So things like deep neural networks, for example, or in general the support vector machines. A lot of discriminative machine learning techniques can be used as well. It's similar thing. So you just learn from the data, but you learn instead of you learn the boundary to be able to look like new data. So again, a new data arrives, ITD pair. I say if it's on this side, so I say this is 50 degree. If on the other side, I say this is minus 50 degree. As simple as that. Right. So the problem, yeah. So it would work. It works fairly nicely in some cases, but the problem arises in reverberant, noisy conditions. Again, the previous plot slide shows you in reverberant conditions, the distribution overlap quite a lot, even at minus 50 and 50 degree. They're quite far apart, but they still overlap. So you want to build a robust sound localization system. Using ITD ILDs may not be enough. And is it possible to extract other better features from the waveform and to increase the robustness of the sound localization system? So that's the first problem. ITD ILDs, they're not very robust. You want to build a machine using these as features. The second, really, these cues, they are explicitly extracted from the waveform. Then the problem is, how do we combine ITD ILDs? As we saw earlier, ITDs is more useful for low frequencies, and ILD is more useful for high frequencies. There's a speech perception psychoacoustics experiment that shows that roughly around 1600 hertz to 2 kilohertz, that's sort of the cutoff threshold between ITD ILDs usefulness. But it's quite blurred line. We don't know how to combine ITD ILD together. And normally, machine systems just put ITD ILD and just concatenate them together as a big feature vector to feed into the machine. Is it the best way we can do? And more importantly, how to combine this binaural cues, ITD ILD, which are binaural cues, with other cues like spectral cues, which is monaural. So how do we combine monaural cues? And this really bothered me for many years. I have no idea, and I tend to just stack all the features together and feed them into a machine. Then it kind of works, but it's not very nice. You just treat the machine learning as a big black box. You don't know really what's going on. So really, what I'm trying to do is again, going back to look at how humans localize sounds. There's a lot of evidence show that humans tend to combine all the cues together. How can we do that? So how do we combine the cues? And is it necessary to explicitly extract cues like ILDs, ITDs from the waveform? And why don't we just use waveform directly for sound localization and let the neural networks work out some cues that might be useful for certain tasks? like some localization. So that's really the motivation, what I'm trying to do here. So let's see how we can do that. How many of you know anything about deep learning or deep neural networks? Oh, that's great. So this is a sort of typical neural networks. So essentially, it's a multi-layer perceptron MLP that people developed back in 80s, 90s. Then later on, we just adding more layers, increase the the number of hidden nodes, and they have very clever algorithm. And most importantly, probably they have just more data, more computing power to make it work. So you have the fully connected layers. Okay, so each the hidden layers is fully connected to each node of the previous layer. Okay, so what I did is using the convolutional networks. So convolutional neural networks is slightly different to a typical neural networks in the sense it has this receptor field and is looking at a local region at a time and doing sort of convolutional computation to convert that local region of the input into a node in the hidden layer, in the next layer. So that's slightly different architecture. This really inspired again by vision. The researchers look at how the cortex for the vision, they find out there's some sort of kind of similar to convolutional layers computation. They have, say, let's say we want to classify or identify if this picture is a car or some other objects. What they do is, we tend to focus on these edges. For example, the edges in the pictures is the most important piece. And so the convolutional layers really is look at, it has these kernels. So these are 2D kernels. And each time you look at a local region in the picture, and you can apply the weight to convert that into a single point in the next layer. Then move this region along the pictures and using the kernels. So what you get is a sort of feature injection process, which convert picture like cars into some sort of representation that's, if you look at these extracted features, you will find mostly they will represent like edges or something.
So just to clarify, because I don't know the answer to this myself, so the kernel obviously gets learned somehow. Is that the same for all positions?
Yeah.
Okay, so that's why you call it convolution.
Yeah.
Okay, thank you.
Well, each local computation is a convolution as well. So the kernel has say a 2D kernels.
Sure.
You just do a.
The kernel's the same and then go through the whole.
Yeah, that's right. But you tend to have multiple kernels, like 32 kernels or 64 kernels.
Okay.
So some kernels will be focused on, say, learning the edges. Some other kernels may focus on learning some other kind of shapes. That's the idea. So is that clear? So you could have multiple convolutional layers. So you can extract some of the features, then you can again apply another layers of convolution to extract further features in a different domain. And then this pooling is one way to reduce. So you think about you've got 32 kernels or 64 kernels. The amount of computation is long, and it tends to overfit the data. So max pooling, you can do a max pooling of, for example, just basically take, say, the window, you take the maximum value, and just it's like downsampling. But the idea of the pooling is you just reduce the it helps the overfitting problem. Then once you kind of do the several layers of convolutional layers, then you can then flatten the output from the convolution layers. So then you can just apply the traditional fully connected layers like MLP layers. This is like a typical neural networks structure to do the classification. So in a way, these convolution layers can be seen as feature extraction. Then once you get some sort of features from the raw picture input, you get some feature, you then feed them into a typical conventional deep neural networks to do a classification task. So how do we do that for sound? So giving a waveform for, say, 1 year, so 11 years, let's say, we can apply for a transform, which is a linear operation. It doesn't throw away any information. So, but what it gives us is the magnitude spectrum and also the phase spectrum. So with the magnitude spectrum and phase spectrum, is it clear? Do that make sense? Yeah. So with phase and magnitude, if you apply invert for transform, you can get the original waveform. So there's nothing, no signal is lost here. So, but we actually did some work directly use the waveform as the input to the neural networks to work out the track features. But this turned out to be more effective if we convert the waveform, the time domain signal, into the frequency domain first. So we get magnitude spectrum, the phase spectrum, but the important thing is we don't throw away any information. We're not extracting any features yet. So this will give you just an idea. So this is magnitude spectrum. So this is really what we call spectrogram. So each slice is one magnitude spectrum. Then you can put all the slides together across time. You get the spectrogram. You can do the same for the phase. You get phase, but it just doesn't look as nice. So I show you for different sound locations. So this is a magnitude spectrum. So let's take a look. 0 degree azimuth for different elevations. And you'll find there's a blue line and a red line. So blue is the left ear and red is right ear signal. So because 0 degree, so there's this magnitude, so the magnitudes spectrum are identical for both ears. But as we move away from this azimuth 90 degree, so the source is can't remember, I think 90 degree, this is on my left-hand side. You can see for different elevations, the left ear and the right ear, they have different spectral. Okay. So show you the phase. So the phase is very difficult to visualize. So this is wrapped phase, so phase between 2 pi, minus pi and pi. So so again, you can kind of see for 0 degree azimuth, phase is identical for both ears. So there's no time difference or no phase difference for both ears. But as you move away, this is elevation 0 degree azimuth, 90 degree. You can see the blue, the curve slightly ahead of the red. So which means sound arrived at my left ear earlier than my right ear. Okay, so that's kind of a phase spectrum. So remember, I can do that for both ears. So I extract phase spectrum and magnitude spectrum for my left ear and also for my right ear. Then stack. So this is left ear and right ear magnitude spectrum. Then I stack phase spectrum for the left ear and the right ear. So this is left and right, this is left and right, magnitude and phase. Then I can apply a 2D kernels, convolutional kernels, to phase and magnitude separately. So I have a set of 32 kernels for the phase, a different 32 kernels for the magnitude, and different 32 kernels for the phase. So if you do the 2D kernels, what you get is a 1D feature. So as they move along, you get sort of 1D kernels. So remember, this is frequency. So as a result, this is kind of frequency, compressed frequency, but this still represents frequency along this dimension.
So it's just the spectrum, it's not the spectrum, right?
No. This is for each frame, each short-term frame. So it's a slice of the spectrogram. So basically, I feed the that sort of features for all the frames into the neural net. Then this allows me to localize for each frame. So I just need one frame at the input that give me a location decision. So once I apply this 2D kernel convolution, I get some sort of features. So this kind of features for each kernel, I get one feature. So if I have 32 kernels, I have 32 features. Then I do some max pooling to reduce the number of features. Then again, I can do another layer convolution to further extract feature. This is very similar to what we do for the vision. So all the convolutional layers is like feature extraction. And so this is really what we use to extract the feature implicitly. So we don't know whether we get it's ITD or ILD. I don't think. But the good thing about this kind of architecture is we do know this sort of feature because we do a 2D convolutional. So it will give me some sort of, because this works with phase spectrum, so it'll give me something similar to the ITD or IPD, so interaural phase difference. So this will be some sort of feature related to interaural phase difference. But the good thing is it combines the phase features with the spectral feature as well, because they work along the frequencies. So this kind of feature really represents a combination of interaural phase difference and the spectral features. Then similarly, this feature will represent some sort of ILD, so interaural level difference, because they work with magnitude between these left and right ears. Then once we have the features that combine ITD, ILD, or spectral cues, I can feed them into my classifier using deep learning. So this is really a plot of, so I'm trying to understand what is being learned by the convolutional neural networks. So this is really a plot for all the kernels that's been learned. Again, blue is for the left ear and the red is for the right ear. This really shows you in learning some sort of structure. For example, that's really learning some sort of phase difference because they have opposite phase. I won't go into any details because of the time, but then once we get down to the second layer, it's quite messy. It's very difficult to understand what's going on. So how do I evaluate these neural networks? So I created binaural simulations using the head-related input responses. There's 4 reverberant rooms we used from this open air or open air libraries. So 4 rooms, one the living room, a church, another church. This is a disused mine in the UK. This is recorded by the people at York. And so this shows you the P60s of reverberation time of different rooms. Then we train the neural networks in the anechoic conditions only. So we don't train the neural net for any of these reverberant conditions. So some results. The blue bars, that's what we call the GCC FAT, which is kind of a classical sound localization system, which didn't do very well because it really designed to localize sound around the horizontal plane. So for the elevation, it really struggled. The orange bars, that's if we train the same neural net but using the phase spectrum only, so we don't give it the magnitude. And again, the orange, the green bars use magnitudes only, and the red is combined both. So it's very clear both phase and magnitude contribute in the performance, and we did fairly well. This is on the frame level evaluation, so we classify each 10 millisecond frame. We're trying to localize the sounds using just 10 millisecond frames. I also look at how the different kernel size. Remember, we have these kernels which expand along the frequencies. So if I reduce these kernels, the feature that would be represents more like the IPD or interaural time difference or interaural level difference without contribution from the frequency spectral cues. So this really shows you kernel size 1 is I don't take into account the spectral cues in the feature extraction. So this is white bars. The colored bars represent a kernel size 9. So you really are playing with different kernel size, see how much contributions come from the spectral cues. Again, it shows, it's very important for elevation, the spectral cues to be able to, the best system really combined IPD, ILD, and the spectral cues. Right, just to summarize, really we're trying to localize sound, avoiding explicitly extracting features like IPD, ILD that we know that's not very robust. So we propose this model that can directly localize sound from the waveform. And the most important advantage of this method is it combines the level and time difference cues with spectral cues altogether in very sort of unified neural network architecture. And they are combined kind of very sort of in a principled way rather than just stack the feature together. And this really improved the performance a lot. So the result I showed you only for elevation localization, but it also works really well for horizontal plane localization. And thank you.
Still have some questions.
Thank you for your talk. Yeah, this is really interesting. I was just wondering your error rate and what it represents.
Yeah.
How do you calculate?
Yeah. So the error rate, so this is if I go back to the evaluation. So I have minus 70 degree, which is down below, and to 70 degree every 10 degree. So from minus, so I have essentially minus 15 classes. So each class represents a angle in elevation. So I got 15 classes. So if it's error, if the frame is from a particular angle, but it's not classified by angle.
Okay, so it's a kind of yes or no. Was it within plus or minus 7.5 degrees or whatever it was?
Yeah. So in this case, it's exactly. You need to be exactly right.
Okay.
Otherwise, so at 0 degrees, so you have 10 minus 10. So if class has 10, that's error.
It's just interesting because sort of doing it that way, you sometimes miss some other information, like so it's kind of like a precision of recall. You're kind of not really, you're perhaps missing some of the false positives or false negatives, is it?
Or reversals.
Do you know what I mean? It's kind of,
Yeah.
I wonder if there might be a better way to kind of assess its performance.
Yeah, I don't think it's relevant because it's a classification. So I have 15 classes.
Yeah.
It's not like a binary classification. You have a threshold that's allow you to say this is right, so this is wrong. So this is really, it's like, I have 15 classes. You have to guess if this represents for a certain class. If it's right, then it's considered wrong. But I did what the error rate or the accuracy then tells you is how badly when you did it wrong, how badly you. So you could be 0 degree, that's the true location, but you localize 10 degree or 90 degree.
Yeah.
So that doesn't tell you. So I also
accuracy, isn't it?
Yeah. So I also computed in the paper. I also presented the RMS errors.
Okay.
So which shows you how far the predicted location is from the true location, but it still works fairly well.
If you go to your spectra phase and amplitude spectra, magnitude and phase one, there was one where you showed them both a bit further on. There was one where you showed for three different, yes, the phase spectrum.
Right.
I was just wondering, using wrapped around phase, for example, if you look at the elevation north, azimuth north, where everything should be the same, you'll notice you've got
some outliers. Yeah.
Well, yes, but they're not outliers because
they're wrapped.
Because it's wrapped, and they're essentially quite close to each other. And I'm just sort of wondering, so two things. One is treating them as completely independent things. And I can understand why you did it from a computational point of view. There would be areas of low spectrum amplitude where you might expect the phase to be quite noisy. So you're going to get a lot of change in phase, which is doesn't actually mean anything. And this issue of wrapping, I don't know quite how you would incorporate the idea that actually minus pi is next door to plus pi in terms of your convolutional recognizer. Which sort of leads me on to the idea of maybe not looking at phase, but maybe delay between the two things. I think there's a model for stereophonic listening. I think it's Fisher, or somebody published in Acoustical Society of America, where he took the left ear filters and the right ear filters and had basically tap delay lines and correlators. And used those as sort of outputs for his. He didn't put it into a neural network, but in a sense that removes the issue of sudden changes, very small things happening that make a big change, which is likely to actually quite significantly throw your recognizer off.
I was going to ask whether these neural nets can accept complex data, because that would be the solution.
But that would be another way of doing it, wouldn't it? Just use I and Q instead of doing it. But do everything at the same time.
That's a very good question. So so back to your first question. That really struck me, how to present the phase, because the wrapping, so I have to wrap the phase, because otherwise the phase just go on forever.
I understand, it's unbounded.
Just to get to work with neural net, you have to normalize everything to a certain range. So phase wrapping is the natural thing to do. But the good thing is the phase wrapping only occurs at the boundary, which is, you can see, it doesn't often occur. So and we're not treating each point in the frequencies individually, because we're doing the convolution, we're doing the integration over frequencies. So that really reduces the effect of the physical phase wrapping. So I think your second question
Well, really, one way out,
And
Jonathan suggested an alternative. One way
the
out
complex,
of
yeah,
that
that's very.
It's not to use phase at all, but is to use some other representation that doesn't have this issue. One way would be to delay what?
Just say it's very non-linear.
What phases?
Yeah, well, it's kind of rapid.
Yes, it is very non-linear. Is to either use I and Q.
I mean, the delay. I mean, that. I think we're trying to use the delay. Yeah.
Can somebody help me out?
Jeffers.
Jeffers, that's it.
Yeah. So Jeffers is a kind of classical model. That's what we use at the beginning to extract this ITD.
Yeah, if you do it explicitly, but I mean, suppose.
So we did compute the cross correlations. Instead of picking the peaks, we compute the cross correlations. Use that as features. So this is really the GCC facts baseline. That's what it uses.
Yeah.
So it uses the correlation function as an input to the neural net. I mean, the reason I didn't compute that is just because this way, we're not just looking at the phase difference, the delay between the two signals, also the phase across spectrum. So I really want to combine both together.
Yeah. So you end up with a big, sort of like a two-dimensional.
Exactly, a matrix rather than a linear vector.
But you could do that with the Jeffers model as well, couldn't you?
Yeah, that was we tried that. It didn't work as well as this model. So yeah, it does occur to me. This really, ideally, we want to unwrap the sort of that point. Really,
that's kind of unbounded. The other thing I did wonder, you used a fixed size kernel through the frequency. Now, as humans, we don't do that.
Yeah. That's a very good question.
Kernel sizes are basically much wider at high frequencies compared, and again, maybe that would.
Yeah. So that's. I mean, the initial idea is, why don't we just replicate, what's happening in the auditory signal? We know the cochlear frequency analysis, for example, is not linear, and ideally, you want to use sort of narrow kernels and wider kernels for higher frequencies. That's not very easy to do just because the convolutional neural net, it doesn't allow you. We did look into that, whether we can customize the layers to do that thing. One thing we did do is instead of having the Fourier transform, we applied a bank of gamma-2 filters, and that's give you the this nonlinear spacing across frequency. So you kind of process that. You still use same kernel size, but because your input is not linear anymore, so it's similar sort of effect. We did.
The other thing is if you're using, like you found the longer spans kernel size work better. One would expect that that's what it would be learning, because it's learning the weight updates across. So it might well be that it's learning the sort of non-linear mapping, not necessarily how humans, but in whatever pattern.
Yeah, that's indeed that's one reason that struck us to look at what the kernel look like. And what we're hoping is we can identify some of the kernel just learn the low frequency sort of features, and some represent the high frequency features. It's a difficult. That's still work in progress. Yeah, we haven't really worked out sort of map nicely to sort of human.
I did wonder, did you try, rather than having two separate paths, convolutional networks, and bring them together later on, one for magnitude, is kind of touches on what these guys are saying, one for phase, why not just stack them so that
so they're all together.
In a convolution of both ears and magnitude and phase at the same time. Because of course that's how, like how you've done it is, in images where it's got RGB, it's got those three different sort of layers. Yeah. Whereas left and right, you could have an extra 2 layers as well.
Yeah. I mean that's we had some conversation with this guy from UCL who's looking at the physiology for sound localization. Really, one thing that struck us is that the Jeffers model is they haven't found enough evidence
No,
in mammals. In birds, there's good evidence, but in mammals, they haven't really found enough. But one thing he found is that indeed there's some sort of cross, like the left input would correspond to some cortex of the left brain, which kind of remind me what you just described. If you can put a left and right phase and left and right magnitude together, to let the neural net learn the left phase with right magnitude, I don't know. That's an interesting idea.
Well, I think more if you combine magnitude and phase together in the same neuron, then if you've got weak magnitude, it'll learn that maybe phase is less reliable when you have weak magnitude.
So that goes back to the complex idea that is something worth looking into, and we had some other similar ideas, really trying to look at. So the guy from UCL, he's interested in ferrous localization because he had a lot of ferrous data. The animal feral.
Yeah, feral.
And one thing we can do is if we provide the neural net with HRTFs measured for ferrets, can we learn something? It will generate some sort of data that will fit his physical horoscope data. So that's another sort of angle that's linked that, because he's kind of have some correspondence to the auditory model. So we want to build that link. But that's quite exciting. I mean, we just did this 6 months ago. So there's a lot of there were there's a lot of that we would like to continue.
It's really interesting seeing the kernels, because I can see you're kind of trying to see if you can learn anything about the process from the network itself, which is nice. I wonder if there's, I don't know much about it, but of course all the ImageNet stuff found ways of extracting feature representations at different levels, didn't it?
Yeah.
I don't know how that works, but I don't know if there's anything.
Yeah, that's what we're trying to do here. It just images are a lot easier to visualize. Sound is just bloody difficult.
Yes.
And there's a lot of like face, for example. What does it mean?
Yeah.
How to visualize face. But we did look into. So there's another line of work I didn't show here. Is we use a waveform as direct input to a bundle of convolutional kernels. And one thing is the output from the kernels, because it's work for the waveform.
The time domain waveform.
Yeah, time domain waveform. We did give it to. So one version is time domain waveform, just fit into a convolutional layers, which essentially does the frequency analysis. Another version is we put in the gamma tone filter bank, get the filtered waveforms, and then fit into convolutional layers. But because of that, you can plot the frequency domain of that output. It's very clear. That's more interesting to visualize, because then you get a special. You can plot all the filters, stack them together, so you have a frequency and filters. So you get like a spectrogram, but not across time, across different filters or different kernels. Then you can see it's emphasizing some frequencies, for example, all the filters. That's quite interesting, because it's clear in the anechoic condition, it just emphasizes the low frequencies, because that's just most effective way. But as we blend in more reverberations, that doesn't work anymore. So it's time to learn more high frequency features. But that's probably it's more it's easier to visualize. We try to understand really. One thing I'm trying to avoid is to use deep learning just as a black box. We're trying to really understand what's being learned and why it is working or why it doesn't.
I mean, I saw this is a very long time ago. A guy called Nigel Allenson at York, and a student, and what they were doing was training this is visual recognition, basically a square array on subsections of this set of concentric rings. So you had basically lines going that way.
Yeah.
And things, and all possible angles of the lines. And they did unsupervised learning, and it was quite interesting to see, because of course you could look at the weights of the neural network, and they corresponded. There was a visual correlator in the weights too.
Yeah.
What it was.
Yeah,
selecting.
that's what they found out is the. I think that's one of the reasons convolutional neural networks
And
become
these are
very.
unsupervised, aren't they?
This is supervised.
Supervised.
This is supervised.
All right.
But there's a lot of convolutional neural networks that were so popular in vision. Just they really show the kernel really learned about these edges around different angles. Essentially, what the vision people do anyway, because before convolutional neural network came up, that they also do the edge detection and these. Again, they explicitly extract the edges, these as features. Now the convolutional neural network just gave them that automatically, and more importantly, is unified with classification later on. So you not necessarily just learn the feature. It could be depending on the task. The feature will be slightly different, rather than you have a fixed set of features for everything. That's really what we're trying to do here. For localization, IPD and ILD may be useful, as we know, but for certain elevations, maybe IPD and ILD become less useful. Some other feature would come up.
These things, these weights, the weights of the kernels on the top half, and just I suppose neural input or something. Yeah,
that's just kernels. I don't remember the size of the kernel. I think it's 9, so you have 9 numbers.
Right.
I think this is 9, the size 9 cross frequency. So I just plot, because the 2D kernels, left and right, one dimension, then the other dimension, the frequency.
Right.
So this is represented 9 FFT bins.
Right.
And then you have left and right. I just plot them separately because difficult. If you've got more features, you can plot them as an image. But you can see, for example, like this kernel is really focusing the high frequency.
Yes, it's not really much attention.
Features, that's really the same. But some others, kind of in the middle, and so it's doing something that's sensible.
Is this the magnitude?
Yeah, this is magnitude. Yeah.
Was the error using gamma features higher than 2FD?
Sorry?
You said you tried using gamma.
Oh, right, yeah.
Was the error worse then?
Yeah, the errors are worse than FFT for now. I think that's because we the gamma tone filter gave you waveform time domain signals as well. We just got say 32 gamma tone filters or 64. You just have 64 waveforms. So this is more compact. We reckon there's something to do with the model's capacity to model the feature rather than Fourier transform is better than gamma tone filters, for example.
How many gamma tone filters do you have?
I think we tried 32 and 64. It doesn't make 64 really. The amount of competition is very, very.
So how many FFT bins here?
This is 256.
Do you think it's probably because of the resolution? Because you have like over 200, whereas you only have like 64 maximum.
That could well be the. But again, we just gamma filter just filter in the time domain. You still have the signal, but it is possible that there's some information being lost. I'm not quite sure that's the reason it didn't work. I think more to do with we just haven't figured out a better way to use gamma-tone filters in convolutional neural network yet.
Any more questions? No? Okay, Steph, then you give us all.